just like
Wait, what's happening?
All right.
I don't want to. No, I don't want to. I'm okay with sharing.
All right, let's continue with Savitch's theorem. So we want to show that non-deterministic space is contained in deterministic space squared. In other words, you can get rid of non-determinism and only pay a quadratic penalty for it. And with respect to time, we don't know how to do that, right? There's still an exponential gap between the non-deterministic time, polynomial time, and deterministic polynomial space. So the idea is to simulate, and we're going to simulate, deterministically simulate this non-deterministic computation and stay pretty thrifty in our space usage. So we're going to aggressively conserve space and waste a lot of time doing that, but the goal is to conserve space, not time. Okay. So consider the non-deterministic computation that's f of n space long. So looking at sideways, you start here at the start state, and then it starts bifurcating into different computation paths, and one of them accepts, and let's say the length of this here in blue, so I'm blue coding it, color coding it. Computation time is bounded by an exponential in the space consumption, right? Because if you use n space, non-deterministic space of a certain bound, it can only change states so many times before it repeats. And because it halts, it doesn't repeat. Because if it repeated, it will just keep going and repeat again and again and again. So these states here along this path do not repeat themselves. If they did, this path will go on forever, right? So we're going to simulate this branch of the non-deterministic computation and all other branches too. Okay, so how can we do all that in a way that conserves space and do it in a deterministic way, right? Being space efficient. And so the high-level strategy will be to use divide and conquer and heavily reuse space over and over again. So here's what that means. So here's this computation path. I'm just showing that one path here. How do you simulate this path? And so this is a non-deterministic, this is a path in a non-deterministic computation from the start state in purple to a red state, final accepting red state. And this path can be very large. Remember, we're doing non-deterministic space computation, so this path uses n space f of n. It uses f space. F is an arbitrary function. But that means it could be using c to the f time, right? Computing in that space. So the path could be very, very long in time, even though it's relatively short in space. It's f of n in space, but it's c to the f of n, exponentially in f of n in time. So here's what we're going to do. Divide and conquer. We're going to pick a random midpoint, and we don't know what it is, so we'll try them all. What is this midpoint? It's a state of the computation, meaning it's some contents of the Turing machine tape. We don't know which is the midpoint, so we're going to try all of them as the midpoint. So we're going to show that it's possible to reach this midpoint state from the initial state, right? And from this midpoint, in turn, it's possible to reach a final state. Which final state? We don't know, so we'll try them all. And that's going to take a lot of time to go through all possible midpoints here. Exponential amount of time, in fact. Because that midpoint is a state not just in the final control, but of the entire tape contents. We're going to try to generate all tape contents to serve as this intermediate step. And for each one of those, verify it's possible to reach from here to here using a valid series of transition function moves. And number two, it's possible to reach from this intermediate state, that final state, using some valid set of transitions. Okay, which will make this intermediate state. So if we pick this correct state as an intermediate state and verify that this is reachable from here, and then from here you can reach a final state, we'll know that that's a valid computation, And then we can just accept. Because such a path exists, we found one. And it could be other paths that are accepting, but we found at least one. Okay, so how do we know that you can reach from this state to this state? Recurse. Do it repeatedly. In other words, find an intermediate state here such that this state reaches here and this state reaches there, and separately do the same trick here. Find an intermediate step here, a state here, such that this state is reachable from this state, and from this red state you can reach that final state. And how do you know that all these 4 red lines are feasible? That they all start and reach the correct pair that they're pointing from and pointing to? Repeat this again and again and again. And by the way, when you first do the green, when you first do this green step here, once you verify that, you can then wipe the slate clean, blank out that space you used to figure this out, and then do this separately in serial. How many understand that strategy? Okay. So we're going to reuse the space in confirming this path that we used to confirm this path. That space will be reused. Now, when we're using the space to confirm this path, we're going to do 2 of these red confirmations in turn. In other words, we're going to use the space to confirm this path, wipe the slate clean, then confirm this path, which will confirm the green, and then wipe the slate clean again and confirm this green, which will mean do this red and then do this red in serial, one after the other, reusing the same space over and over again. And how do you confirm the red path? Bifurcate again, break it in the middle, divide and conquer, and just keep doing this. So there's a lot of reusing of space here, very, very dramatic reuse of space. How do we know which midpoint to try? Try them all. How many are there? Exponential number. That's okay. We got time. We don't have space, but we got time. Space is scarce. Time is plentiful. So we're wasting a lot of time reusing and reusing and reusing the same amount of space so we don't waste too much space. So the recursion stack depth is at most the length of this path. How many get that? Because you're recursing on the midpoint, then the midpoint of the midpoint, then the midpoint of the midpoint of the midpoint. And how deep is the recursion stack when you recurse like that? It's the logarithm of the original path, because you're only picking midpoints. And when you finish with this recursing on this half, you wipe it clean and then just recurse on this half. You don't have to recurse on both simultaneously. So the stack gets reused and reused. All right? So you recurse logarithmic number in the length of this path. But how long is this path? It's c to the f. So the log of that, the recursion stack, is just roughly big O of f. Right? The log of c to the f is roughly f. So the recursion stack depth is f. How big is each frame on the stack? How much stuff you need to store in the stack for each frame of the recursion? Well, it's the entire contents of the tape. How big is the tape? F. Right? So you have the stack is f deep, and each frame of the stack is roughly f wide, which means the total amount of space you use in this deterministic simulation is f times f, which is f squared. And there's your theorem. Okay. Now, if you don't have any questions at this point, you probably don't understand it. So ask me some questions. Yeah.
Why is this stack frame size f?
Because you have to remember this intermediate step, and that's a state of the entire machine, including the tape. And the machine has f of n tape.
So you need to have all of the tape in order to know which position you're in.
Yes. In order to remember which state you were in so that you can then pick this state and see if this state can reach this state, you need to have both states.
There's no encoding, other encoding.
Well, you can do plenty of encoding, but the tape can have arbitrary stuff on it, including all sorts of random things, and there's no way to compress it in general. And so you have to be prepared to copy the entire tape over and over and over again as you recurse. But the good news is you only recurse a logarithmic number of times in the length of the time bound. And the time bound is exponential and the space bound. So it's a log of the exponential, which is just the space bound originally. And each stack frame is therefore the entire contents of the tape of the Turing machine, and there's that many of them to recurse on, so it's the square of that total amount of deterministic space needed to execute this entire simulation. And this simulation is horribly slow. Because at every point when you pick a midpoint, you don't know it's a midpoint or not the midpoint. You pick all possible midpoints, which are all possible states that the tape can be in, exponential number of them. And that's just to find the green point. To find the red point, you do that again. And to find this red point, you do it again. And then to find the midpoint between here and there, you do it again and again and again. All possible ones. And you just cycle over all of them. Brute force. This is like really, really brute force here in terms of time. But in terms of space, it's pretty tame because we're using the same space over and over and over again. And by the way, if this red path here is the same as this red path here, because this state is the same as that, you're going to compute it twice. You're not going to remember that you computed it before because you do it from scratch every time without remembering, just by storing the midpoints. How many understand that? There's a lot of waste going on here in time, but a lot of thriftiness in space. It's a very dramatic trade-off here between space and time in favor of space and to the detriment of time. But it works. And so anything that you can do in space f, non-deterministically, you can do in time f squared, deterministically. Because this simulation is deterministic. You're trying all possibilities. So what have you done here in this non-deterministic computation here? You basically saw if there's a way to connect this state with some final state in whatever set of intermediate state transitions that you care to choose, and you've tried them all, then you can accept. Otherwise, you reject. And by trying all of them and all final states, you check all the possible paths in this tree of size f of n. Excuse me, of size c to the f of n. That's the length of the path in time. The amount of space is f of n. The length of this path could be exponential in the amount of space that this non-deterministic computation uses. So that's the theorem, basically. That's all the details. Now, you can add more and more details here and low-level details, but that's all the ideas are right there on these two slides. And that's Savitch's theorem. It's probably the most aggressive reuse of space that I've ever seen. There's a lot of waste going on. This deterministic simulation will go through all possible tape contents, even ones which are not even feasible for the machine to read. It'll try those too. All possibilities for every single intermediate point. So you'll try all possibilities for this point and all possibilities for that point in combination with this point, and for each one of those, all possibilities of the intermediate, and on and on and on. And just to check one of those paths and to check the next, start all over again. And then finally you'll have the green one. And finally, and then at the end you'll know if there's a, so it's almost a graph reachability problem where you reconstruct the graph over and over and over again, and you see if there's a way to reach from the start node to the end node. When the graph is not fully defined as a whole graph, at any given moment you keep recomputing the nodes of the graph. Exponential number of nodes in this graph. How many understand that analogy? So it's a graph reachability problem here. You want to see if you can reach this node from that node when you don't have the graph all at once. You have to recompute pieces of the graph that you need them on the fly as you need them. And these nodes in the graph are states of the entire tape. All possible states. All possible strings that can be on a tape at any given moment, and the tape is f of n long. So it's c to the f of n, different possibilities at every stage, and there's lots of stages. Okay, so that's what's going on here. That's how aggressive the trade-off can be between space and time when you want to save one in sacrifice of the other. Is it worth it? Well, in practice, no, it's not. But in theory, it's possible to do this. And it's not even clear that in theory it's possible. right? Some people optimize their lives very, very aggressively in terms of time versus money. Some on one end of the spectrum versus another. I'll give you examples. Some people drive across town to buy some grocery on sale at some supermarket that's 10 miles away. They save a couple of dimes, per pound on some potatoes or whatever's on sale. So they save some money, but they're spending a lot of time doing this. That's an example from real life where you may not want to do that, right? You don't want to drive across town for cheaper gas if the amount of miles you're driving, which takes you gas also, is almost what you save. But some people will do that. They spend hours clipping coupons to save a few dollars on their grocery. I'm not belittling this behavior, by the way. I'm just giving you examples of what people do. So they spend hours clipping coupons, not realizing that if they took those hours and worked during those hours instead of clipping, they'll make a lot more money that they're saving clipping the coupons. Now, if they enjoy clipping coupons, that's a different story. They're optimizing something else. That's their hobby now, and I don't want to, criticize their hobby. In fact, I'm not criticizing anything. I'm just giving you examples. Other people do the other way around. Some people make so much money per hour, that time is so valuable, that when they search for a parking spot, they just park somewhere illegal, they take the ticket, and that'll cost them less than if they spend an extra 15 or 20 minutes looking for a parking spot far away and then walk for 10 minutes and then 10 minutes back. They're better off getting a $50 ticket. Financially, they're better off. So that's another optimization in the other direction. And then other people pick other points in the trade-off curve between time versus money. And people even understand that. They say time is money, right? You've heard all that expression, time is money. What do they mean? It means you can convert one to the other fluidly. And because you can, you have to do it judiciously and pick the right point on the curve and not end up wasting your time or wasting your money unnecessarily. Okay, so there's an example of an extreme trade-off between space and time in favor of space and to the detriment of time. Sometimes it's the other way around. Sometimes by using more space, you can save a lot of time, and we'll see examples of that too. Okay, any other questions or comments on this? This is not an obvious theorem, right? It took some cleverness to realize this. And again, what is this theorem? It's the analog of P is equal to NP. The relation between non-deterministic time and deterministic time, that's still open for 45 years. But the relation between deterministic space and non-deterministic space, there it is, and there's the proof. That's not open. It's been known since 1967. And the guy who did this was Walter Savitch. And suffice it to square. Now, is it possible to do in less than square? We don't know. That's not to say it's impossible to do it in, f to the 1.9. Maybe it is. But that's the best we got so far after 45 years of people looking at this. But the point is, squaring it suffices. We're not saying it's necessary. So it's an upper bound, not a lower bound. And not an exact bound, necessarily. Okay, any other questions or comments on this? This is a non-trivial theorem. It's amazing it even works, actually. If you look at it, it's so aggressively reusing space. Yeah.
So is there any overhead for finding that target path?
Well, yeah, the overhead is you're going to pay exponentially in time. And how do you know where the target path is? You don't. So you try all possibilities. Did I not answer it? Okay. What do you?
Is this done on the run of the machine or?
On what of the machine?
The run of the machine.
What do you mean the run of the machine?
On an input.
So what you're doing is there's a non-deterministic algorithm or machine that's designed to accept this language, and it's running in non-deterministic space F. Now, you're simulating its execution by not executing it directly, but by executing it indirectly. you want to see if there exists you want to see what this machine will do on a given input. So you have the input and you have the machine. So what you're doing is you pick an intermediate state that the machine can be. And from that intermediate state, you see if it's possible to reach this intermediate state from its initial state. And secondly, from its intermediate state, it's possible to reach a final state. So you're sort of doing a meta-analysis on this machine. You're not running it. You're sort of analyzing it. So if this machine was in this state with the contents of the tape being such and such, with the read-write being right there, according to its transition function, is it possible to reach this other state? And how do you determine that? Again, not by simulating it directly, but by picking another midpoint and saying it's possible to reach this midpoint, and then from this midpoint reach that, and then you'll know the answer to the green. And separately, you figure out the answer for this green by doing the same thing here. How do you find out the answer to the red? Recurse again and find another, purple point, here, such that this will reach here, this will reach here. Then you'll know the answer to the red. Then you do again the same thing with this red. After wiping clean the slate, the memory, and then you'll know the answer to the green, and then you do the same thing for this other half recursively. And there's a lot of recursion going on. And you have to keep track of all this recursion by keeping track of the stack. That's going to take the simulator some space. How much space? Quadratic in how much the original machine takes. And you're going to try all possibilities for each one of these mid-waypoints. And I'm reluctant to call them midpoints, because mid is a bit of a misnomer. It means that this distance is the same as this distance. It's not necessarily. You have no way of ensuring that. It's more like a waypoint in between. It's not necessarily the midpoint, like merge sort. How many understand that fine point? It's not necessarily the midpoint. Just kind of calling it an intermediate point, not necessarily the middle of this path. And if there's a path from here to here, you will discover it. You will stumble across it at some point. What's the assurance that you will stumble across it at some point? You won't miss it? Because you're trying all of them. You're being so exhaustive, you won't miss anything. But that'll cost you. That will cost you heavily and dramatically in time to try all possible intermediate points. Yeah.
Do we have to remember the midpoint, the last midpoint we tried?
Yes, you have to remember the last midpoint. That's why you got to keep all the stack frames over those midpoints. But remember how recursion works, right? In merge sort, right? You do this half, and then recursively you do this quarter and that quarter, and recursively then this eighth and that eighth. How deep is the recursion stack in terms of the original n numbers that you're trying to sort? Log n. So you got to remember log n waypoints as you recurse.
And where is the stack on the tape?
You're storing it on your tape. You're the simulator. Yeah, and each stack frame is a copy of what you're simulating, its entire tape. So you have f of n stack frames, each one f of m large. That's where the f squared comes in, right? Each recursion stack is size f of n, and you have f of n of them. So that's where so your space will be the square of what you're simulating, the square of the space that you're simulating. And so a lot of these waypoints will be the same as other waypoints. How many get that? Yeah, that's okay. It's very wasteful in time. Thrifty in space. This is the ultimate in coupon clipping here. You're going to be spending millennia clipping coupons just to save a few pennies. I'm not saying this is practical. I'm saying this is possible. And it's not even clear that it's possible before you see this proof. Because for P is equal to NP, we have no idea how to do this. And for other space bounds and other space deterministic versus non-deterministic, we still don't know how to do this. Right? And other resources, again, all bets are off. You have to kind of treat them on a special kind of basis. Okay, so yeah, question? Yeah. So basically this says, as a corollary, that non-deterministic polynomial space is the same as deterministic polynomial space. Why? Because when you start taking the union of all the non-deterministic space complexity classes to give you n space, this is what the definition of n space is. The previous theorem, Savitch's theorem, showed that suffices to square each one of these to get you into a deterministic class. So the union of all the squares of all these classes deterministically is the infinite union of all these classes without squaring them, because they're all there. Right? So this is just d space n to the k, and this space n to the k is just p space, so both of them are equal to p space. And that's why when we say p space, we don't differentiate between n p space and d p space, deterministic polynomial space and non-deterministic. Now you know why you just call it p space, and we don't have two different ones. For time, we have two different names, p and np. If it turns out that we're both the same, we would just call them p, both of them, and not p and np separately, right? So polynomial space is invariant with respect to non-determinism. Non-determinism doesn't affect it, interestingly enough. Polynomial time, we don't know. It's been open 45 years. So this is the analog of p is equal to np for space, not time. And it took 2 slides to prove it. You know, very few things in this class take 2 slides to prove, if you think about it. Even the halting problem proof was only 1 slide, right? Any more questions? Yeah.
Why are lower bounds harder to prove?
So lower bounds are hard to prove because you're trying to prove you're not a millionaire. You want to show that no possible algorithm in the universe, however complicated or clever or convoluted or billions of lines of code of it, will possibly work. To show an upper bound, you just have to show one thing that works. To show a lower bound, you have to show that an infinity of things don't work. So that's a lot more work to argue about an infinity of cases as opposed to one case. An infinity of cases that don't work versus only one case that does work. So again, to prove that you're a millionaire, show me the money, and that's a proof. Here's a big pile of cash. It's mine. I'm a millionaire. That's a very simple proof. I'm not saying it's easy to get the money, but once you have the money, it's easy to prove that you got it. To show that you're not a millionaire, you can't just not show me the money. That's not a proof. Maybe you own a winning lottery ticket. Maybe somebody was very generous to you in their will, and you don't even know it. Right? There could be all sorts of ways to be a millionaire. Without even knowing it yourself, much as being able to prove it to other people. Right? Maybe you're about to win a lot of money in some hush money deal for some non-disclosure agreement. I'm not saying who and what, but you know, maybe you have a lot of money coming your way. And it's, you know, so proving that you're not a millionaire is hard. You have to cover a lot of ground, and no proof is really very convincing, even in real life. So to show that p is not equal to np, you have to show that no possible clever scheme like this will possibly work. But we just showed that np space is equal to p space. And to do that, all we had to show is that one thing worked, and it was this thing. We didn't have to argue about an infinity of other possible clever schemes at the same time. And for algorithms too, you know, to show that n log n is a lower bound for sorting is not easy. I mean, turns out we can do this, but that proof has to apply to all possible ways to sort. And even then, it only applies to comparison-based sorting, not to arbitrary ways of sorting and things like that. So that's what this is. Okay, any other thoughts or questions about any of this? All right, so moving ahead, so deterministic space, we know that deterministic space is closed under complementation. That is, if you take the complements of all the languages in D space, you get the same class. Now, this one is particularly easy to prove because it's deterministic. So how do you prove this? Well, if you can decide the language in a certain amount of space deterministically, to decide the complement of the language, what do you got to do? Something pretty straightforward, simple. Do what you did before and just flip the bit. Flip the answer around. If you're going to say yes, say no. If you're going to say no, say yes. That's it. So if you can do something in a certain amount of space, you can flip it around. if you can do a certain amount of deterministic time, you can flip that around too. So the complement of the deterministic time language is the same deterministic time again. So that part is easy. So you can just simulate and negate. But here's the hard part. If you're doing something in non-deterministic space, and you want to complement that, you can't just compute the answer and complement, because the answer is there exists some path. You can flip it around and couch it in another existence of some other path. You want to show that no path exists such that. So it becomes a for all, not a there exists. Okay, and that's generally very hard to do, to complement a language that's in a non-deterministic class, time or space category. But Immerman in 1987 managed to do this for non-deterministic space. He showed that non-deterministic space S is the same as the complement of this non-deterministic space S. In other words, the set of complement languages in this class is the same as the languages in this class, the exact same set. So it's non-deterministic space is closed under complementation for any space function S. Okay, that was not easy to do. That's kind of a similar argument to Savitch's theorem. It's a lot of reuse of space in very clever ways to make it work. Remember, Savitch's theorem is about non-deterministic time converted to deterministic, non-deterministic space converted to deterministic space of the square of the original space by squaring the space. This is non-deterministic space is the relationship with the complement of all the languages. The class of the class corresponds to the complement of all the languages, not converting determinism to non-determinism or vice versa. So it's very similar to Savitch's theorem in terms of structure. But this took a while. Remember, Hartmanis and Stearns proved their stuff in the mid-60s. It took an extra 20 years until the 80s. In fact, when I was a graduate student, I heard about this proof. It was just recent. You know, it's kind of news because I was a graduate student roughly in the late 80s. Now, for time complexity classes, it's all wide open. We don't know if complementing all the languages in a particular time class results in the same class. So we don't know in particular if NP is equal to co-NP. In other words, all the complements of the languages in NP, we don't know if it's equal to the same languages in NP. Maybe, maybe not. And interesting consequences will follow in either case. Right? So for example, if NP is not equal to co-NP, then from it you know that P is not equal to NP, because P is equal to co-P. Right? And there's a book I put on the website by Kozan, Theory of Computation. This is a more advanced book than the one we're using in this class. So this is like for hardcore, complexity theory kind of gurus. And it's on the reading list. It's not required, but you could look at it for extra credit. And in lecture 4 on in this book, they actually prove Immerman's theorem. That non-deterministic space is closed under complementation right there. And there's the proof. That's the whole proof. It's only a couple of pages long. So it's not that long. It basically kind of mimics Savitch's argument. And on the cover of this book, called Descriptive Complexity, you see Neil Immerman's book, where you have this proof again in his own words and a bunch of other results too. So these are very advanced, computational complexity complexity theory books, sometimes called descriptive complexity. And there's the Chomsky hierarchy on steroids, different than the picture I use. I kind of animate it and show it with colors and so on. And they show, so here's the log space, right? This is called Nick's class. Here's P, here's NP, here's P space, exponential time, recursive functions, so these are like decidable functions, or actually recognizable functions right here. And here are recursively enumerable functional recognizable languages. Here's a lot of other more complicated languages, including Turing degrees, and so on. And all of this is 2 to the sigma star. So this is kind of a different way of depicting the Chomsky hierarchy. And here are the regular languages, by the way, right here. Right. I like my picture better, and I'm kind of maybe biased a little bit. And a lot of these classes we haven't mentioned and we won't mention in class. Some of them we have and we will. And so there's NP, there's co-NP. Here's their intersection. and their intersection contains P and perhaps contains other things too. We don't know. That's open as well. There's a lot of open questions. Anyway, for extra credit, you can download this book. It's on the class website. You can look at it, tell me what you think, see what you can get out of it. If you want to go more advanced, deeper dive into all these things, it gets pretty esoteric pretty quickly. Right? And here's that diagram kind of expanded out a little bit more so you can see more details. But it is on the cover of the book. All right, so again, back to the Chomsky hierarchy, just to put this in context. So we now know what P and NP is, and there's the theorem right here. Right? Polynomial space deterministic is equal to non-deterministic polynomial space. Right? That's a consequence of Savitch's theorem, and it's equal to the complement of non-deterministic polynomial space. That's a consequence of Immerman's theorem. So there's two theorems we just proved right here. So now we can add these red to this P space that we had before, because these are just other names for the same class. Now you know. And exponential space is the same as co-exponential space. It's also a consequence of Immerman's theorem, because these classes are closed under complement. So now we can put more detail, fill in more details here, and that's what's being depicted on this slide. These two new kind of characterizations over here, and there'll be more stuff added to it pretty quickly. So here's kind of an extra credit question. Can you enumerate all Turing machines for all languages in P? Now, what we're saying here is, can you construct a Turing machine that spits out descriptions of Turing machines? And among all these Turing machines that you're spitting out their descriptions, all of P is covered. But none of the languages outside of P are covered. In other words, it's all of P and nothing but P in terms of the union of all the languages of all these Turing machines that we're outputting. Okay, so we want to output Turing machines for each and every single language in P, but no Turing machines for languages that are not in P. The question is, can you do that? And can you do it for other complexity classes like NP or P space or exponential time or exponential space? And I'm saying you don't have to necessarily do it in order. Right? So in lexicographic order, it'd be undecidable to do. So I'm not asking you to do the undecidable. But if you want to do it not in lexicographic order, just keep spitting out descriptions of Turing machines that cover all of P eventually. Every language will eventually be covered by a Turing machine that you will print out, and your algorithm is guaranteed to do this. The question is, can you do this? And I'll give you a hint. Yes, you can do it. The question is, how would you do that? How many even understand the question? I'm just curious. Okay. Any questions about the question? Any meta questions? What am I asking you to do? Yeah.
So the languages in P here, we're talking about decidable languages.
So all of P, all the languages in P are decidable. In fact, they're more than just decidable. They're decidable in polynomial time. More than that, they're decidable in polynomial time deterministically. So they're more than just decidable. They're decidable in polynomial time, and they're decidable in polynomial time deterministically. All the languages in NP are also decidable, but they're decidable deterministically, non-deterministically in polynomial time. Now, how do you decide all the languages in NP deterministically in polynomial time? That question is worth $1 million. We don't know. So they're all decidable languages in P, in NP, in P space, in exponential time. They're all decidable. That's the beauty of it. There's algorithms for all of them. Not necessarily efficient algorithms. And whether the algorithms are efficient for some of them, most of these are open questions. Yeah.
I have two questions.
Yeah.
One is, if you enumerate a machine, can it point to the same language?
Sure. Yeah, that's a good question. So not only I'm not necessarily enumerating in lexicographic order, but some languages may be hit many times. In fact, an infinite number of times if you'd like. So you can have machines that will all hit the same language, as long as there's other machines that hit the other languages too. And they won't be arbitrarily delayed on your list. That's okay. Yeah.
Given a class and given a machine, can we check if it belongs to that class or not?
Undecidable. Why is that undecidable? Rice's theorem. I'm so proud of you. Yeah. Now you're getting it. The force is strong in you. What else? More questions? Yeah.
Is there a P-complete?
Yes. There are languages that are NP-complete, there are languages that are P-complete, there are languages that are P-space-complete, there are languages that are log-space-complete, and exponential time-complete, and any class has dash-complete problems in it. It's not just NP-complete. Those are the ones we know and love and talk a lot about. But every class had a core of problems that are complete for that class. And they're all different than one another. All these complete classes, subclasses. So for extra credit, take a crack at that. You know, who knows? Maybe I'll put some of this on the final. I haven't decided yet. Okay. Let's split more hairs. So we already saw there's an infinite space hierarchy, infinite time hierarchy, and each level of the hierarchy is populated by an infinite number of languages that were not in the lower levels. And so it's an infinite number of levels with infinite number of new languages in each that aren't below. And there's no contradiction there. It's a lot going on. Right? So if you have more space, you can recognize more languages. If you have more time, you can recognize more languages. Everything is decidable. All the languages we're talking about are all decidable, but taking more and more space and more time to decide. So here's a fine hair-splitting point. How much more additional space do you need to get more languages? Because if you have an extra 20 bytes and that's it, it's not enough. It's not a asymptotic increase. So what if you have the square? That's enough. What if you have log times more space than before? What if you have log times how much space you have? Is that enough? You see what I'm saying? It's like how much more space or time do you need that for sure you'll get more languages? Because we already know that some languages are outside the class, but we don't know how far outside the class they are in terms of how much more space do you need and time you need. We just know that there is some amount that will be required more in terms of space and time, but not the minimum amount. We don't know the minimum amount. How many understand the point? Okay, now we're about to go into the fine, minutia. We won't prove a whole lot here, but for space, I'll just tell you what the results are. As long as one is little o of the other, that's enough. As long as it's asymptotically greater, I don't care by how much, very little. Like if one is s and one is s log s, that's enough. Or if one is s and one is s to the 1.0001, slightly larger than s, that's enough. You get more languages automatically. And the way to prove this is exactly the same argument as before for the hierarchy theorem, space and time hierarchy theorem, except when you diagonalize, try to do it efficiently. Don't just waste a lot of space and time doing the simulation. Just do it very thriftily. And it turns out a little bit of extra space, however little, as long as it's asymptotically more, is enough to get you new languages that you could not recognize with any lesser space than that. And by the way, I keep making these comments here, which I haven't mentioned explicitly, but the time and the space bounds themselves must be computable functions. We took that for granted up until I just mentioned it now. But when we talk about time-bound T of n and space-bound S of n, I had it on the slides, but I didn't make a big deal of it until I'm now splitting this hair. These functions T of n and S of n themselves need to be computable. There's got to be algorithms that compute it. If the time or the space-bound are themselves not computable, all bets are off. Weird things can happen. And these theorems don't necessarily hold. Yeah.
You can have algorithms for which T of n is uncomputable, but the algorithm itself is.
No. If T of n or S of n are uncomputable, the simulations begin to fail. Why? Because part of the simulation is to watch the space like a hawk and see if you ever exceed that space, or watch the time like a hawk and see if you ever exceed that time. But how will you know if what you're simulating exceeds that time if you can't even compute that time? Because it's an uncomputable function. And we already know there's plenty of uncomputable functions. So if your time-bound or your space-bound are themselves uncomputable, you're going to have trouble doing the simulations that are part of the proofs. And the proofs begin to break down and they don't actually hold anymore. And not just the proofs break down, the theorems themselves are no longer true. we'll talk a little bit more of that in a second. Weird things can happen. But all functions that we know and love and you're familiar with and that you've used in your life are not uncomputable. Squaring something is definitely computable. Cubing, exponentiating, taking the factorial, taking the log, taking the sine, the cosine. These are all computable functions. So usually you don't have to worry about this fine minutia of a point. But I'm just bringing it to your attention. It could become important if you really are talking about arbitrary space and time-bound functions that are really weird in and of themselves. Then you get all sorts of weird behaviors that are not a fact of the languages you're dealing with, but of the actual bounds that you're trying to apply to the computations that recognize or don't recognize or decide or don't decide those languages. Things can go awry. It's a technical point. It's not a main point, but I'm just letting you know that's an issue. Yeah.
So it is possible to have like a T event where it's not computable, have that bound to encapsulate all the decidable languages?
No, that's still not possible, actually. But what you can have is some weird enough T such that deterministic space T of n is equal to deterministic space 2 to the 2 to the T of n. That you can have if it's weird enough T. In other words, this seems to contradict the space hierarchy theorem. Whereas if you have more space, you can recognize new things. It can't be the same class as, when you have less space asymptotically. But if T is weird enough, that can happen. And if the time or the space bound is weird enough, you can have these pathologies both in space and in time, in apparent contradiction of the space hierarchy theorem. But let's take another quick look at the space hierarchy theorem. Look at this note in purple. S of n must be computable and everywhere defined. I didn't highlight that before. I'm highlighting that now. This is the slide we looked at earlier. And while we're doing that, let's look at the time hierarchy theorem again. And guess what it's going to say there in the fine print? The time must be computable and everywhere defined too. So now I'm reading you the fine print here. I didn't harp on it before because it's enough to chew on without even harping on this minutia that would obfuscate all the rest of the more important details. But now we can go back and pick up this detail.
Even if it's not computable, does still the theorem hold?
No, it doesn't hold actually. Why doesn't it hold? Because, like I said, there are some weird enough time function t such that 2 to the 2 to the t is this time-wise is the same class as t. And that's not what the theorem says. The theorem says, especially the denseness versions, is that if you have a little bit more space or a little bit more time, you can recognize brand new functions or languages that you couldn't recognize before, that you couldn't decide before. So let's now harp on that for a little bit. So how dense is the space hierarchy if you have a little bit more space? In other words, if S1 is big O of S2, you can recognize stuff in S2 that is not in S1. There are languages that are in this new, slightly larger class, S2, right? The deterministic space S2 that are not in the deterministic space S1. As long as S2 is slightly larger than S1. That's what the theorem says. Now again, here's that caveat, that S2 and S1 must be both computable. Okay. So the space hierarchy not only is infinite, it's dense. Because it was infinite if you had to maybe multiply the function, the bound, by a linear factor, like n squared and cubed, and then you get more languages every time you multiply by n. That would still be infinite hierarchy. But it's worse than that. If you multiply it by square root of n, or log n, or n to the 0.0001, keep multiplying by, you still get more and more functions at every level, and an infinite number at every level, so it's infinitely dense. How many get that? There's a lot going on here. So not only I showed you an infinite number of levels of time and space complexity, each two different time and space complexities, have an infinite number of levels in between. And each level gets you a new infinity of languages that were not available at the lower level, however close to that level it is. So so space is very dense. Suffice it to just go up a little bit. So I'm giving you some examples here. So for example, log space is contained in log square space. And that's a proper containment. It's no longer a subset where equality is optional. Equality here is not optional. Log squared space contains definitely is a superset, proper superset, does not contain just log n, but contains other things that are not in log n. Similarly, n is a proper subset, proper, emphasis on the word proper, subset of n log n. N squared is a proper subset of n to the 2.001 because it's dense. In fact, n to the x is a proper subset of n to the y as long as x is slightly less than y. It doesn't matter how. Could be smaller by 1 over Google. And if they're both exponents, that's enough. There's an infinite number of languages all of a sudden are possible to decide. So we know as a corollary that log space is not equal to polynomial space. That much we know. Because this is log and this is polynomial, and log is asymptotically less than polynomial. So by the space hierarchy denseness, this is an inequality. How many get that? Yeah. And same for p space and exponential space. We know that p space is not the same as exponential space because exponential is asymptotically bigger than a polynomial, and that's enough to get you more languages. In fact, it's more than enough. Even slightly larger than polynomial, but not quite exponential. There's plenty of functions that are larger than polynomial, but are smaller than exponential. Give me a function that's larger than polynomial, but smaller than an exponential. Just so you don't think that there's only polynomials and exponentials and nothing in between. Give me one. Slightly larger than polynomial, slightly smaller than exponential, asymptotically. Factorial is more than 2 to the n, actually. It's n to the n. But it's a good try. He spoke up. He gets points for courage. That's good.
2 to the square root then? No.
So what else?
2 to the n over n.
2 to the n over n? That's still exponential. Because that's larger than 1.99 to the n. And that's already exponential too. But it's another good try. What's it? N times log n? That's bigger than n, but smaller than n squared. So it's still polynomial. It's bounded between two polynomials, which makes it polynomial, even though it doesn't look like a polynomial, n log n. Keep going. Yes. N to the log n. How do you know it's bigger than any polynomial? Because any polynomial has a constant in the exponent. This is not a constant. This grows. But this is not as big as an exponential. It's just bigger than all polynomials, but smaller than all exponentials with any base, interestingly. And there's many others. I'll let you figure out more. Okay, so we know that p space and exponential space, polynomial space and exponential, are not the same. We know that logarithmic space and polynomial space are not the same either. There's separation between those classes. Now, an analogous question is how much more time does it require to get more languages? We just did the exercise for space. And it turns out for time, you can show a logarithmic factor more is enough. The denseness in time is not as tight as the denseness in space. In space, the slightest exponential, the slightest asymptotic increase is enough to get you more languages. In time, the increase needs to be at least a log factor. Right? So there are, given two time bounds T1 and T2, as long as T1 log T1 is little o of T2, there are languages in T2 that are not in T1. So you get this extra log factor. Why is there a log factor in space and not in time? Let me give you two different considerations here. One is that space was reusable. Time isn't. So a little bit of extra space is worth more than a little bit in extra time. How many understand that intuition? It's not a proof, it's an intuition. Because it's reusable, it's worth more. You can do more with it. It's more versatile, more powerful. And having said that, this is here we're saying that log factor is sufficient to get you more languages. We're not saying it's necessary. We're saying it's sufficient. It could be the case that less than log factor is also sufficient. We just can't prove that. It's an open question if log factor is actually necessary. Here we're only saying it's sufficient. If you go out by a log factor, you get more languages. If you go out by less than a log factor, will you get more languages still? We don't know, in general. Yeah.
So it could be the case that like denseness is just as uniformous for space.
It could be the case. We can't prove it isn't. But with space, it happens to be easy enough to prove that we have a proof for it. In fact, like Hartmanis and Stearns actually proved that too. The proof is very similar to the proofs we saw earlier for the hierarchy theorems, except if you just have to see how much more space you need to do the actual simulation, to compute this language L that kind of contradicts itself when you feed its own index to itself and so on. If you do all that and you do it thriftily, if you try to conserve space, a little bit more space does the job, gets you there. But with time, you have to spend a little bit extra time. Why? Because you have to count in the simulation how many steps that simulation takes. And when it exceeds the time, the allotted time, you can cut it off. How will you count the time? Well, one way to do it is to keep a counter. And if it goes through T event steps, how long will it take you to count all those steps? Even if you have an extra tape for the counter will be logarithmic in the number of times the clock ticks on this simulation. If it ticks T times, it takes you log of T to keep the counter around, because every time you count, you may need to do a carry ripple of the count, and the counter is log of T long, and every time you count, you may need to touch many of the bits of the counter because you get ripple effect, as you keep adding to the counter, and you do the simulation while you're doing all this. So for every step of the simulation, you may have to do, log steps just to keep the count. How many sort of get this intuition? Now, does that mean you have to do it this way, and that's the only way to do it? We don't know. But that's one way to do it, and that works. And so we get this result. That by keeping a counter around and getting charged for the counter like this, we can keep track of time and cut it off when we want to, and everything works. Is there a clever way to do it without the counter? Are we using a smaller counter or multiple smaller counters that will, who knows? That's what is difficult to show, right? And we can't show that that's the best you can do because that's proving you're not a millionaire. Again, no other cleverer way of simulating while counting, could be more thrifty in the use of time. So again, the proof is very similar to what we've seen earlier. So the hierarchy is infinite for time, but not quite as dense as space. Space is very, very tight. Time is a little bit looser. It's got log factor jumps, but it's still infinite. And it could be denser than that. We just don't know. So for example, linear deterministic time is in proper subset of n log squared time, and quadratic deterministic time is in properly contained in deterministic time n to the 2.001, because that's more than a log factor. If you increase the exponent even slightly, that's better than the log. Grows faster than log, right? And deterministic time 2 to the n is inside properly deterministic time n squared 2 to the n, or even n 2 to the n for that matter, and so on and so on. So a corollary of this is that logarithmic time as a class is not the same as polynomial time, because polynomial time is bigger than log time by at least a log factor, actually much more than that. Actually, what's the relation between polynomial and log? How much bigger is linear than the log? Not a trick question. How much bigger is n than log n? One word. Exponential amount. Yeah, it's very dramatic. It's not just a little bit bigger, it's hugely bigger. The bigger between n and log n is the same difference as n and 2 to the n. They're both two exponential jumps. So log time is not the same as polynomial time, which contains linear. They're very, very different. P has so much more in it than log time. And of course, exponential time has a lot more in it than polynomial time because that jump is exponential also. And by the space dense hierarchy results theorem, there's a huge gap there. Okay. So we know that log time is contained in log space, and log space contained in non-deterministic log space. This is the deterministic log space, L. So we know that non-deterministic log space contained in P is contained in NP, NP is contained in P space, and so on and so on. These are all containments. Now, why is this containment true? Log time is in logarithmic space because you cannot use more space than you have time to use. That one is pretty obvious, the first containment. Why is this containment true? Because non-determinism is a special case. Determinism is a special case of non-determinism. So if you have non-determinism in log space, that's at least as good as determinism in log space. So that's why this second containment is true. How many see that? We're proving them all after the other based on the results. These are all corollaries to the theorems we just proved. Right? Non-deterministic log space is contained in polynomial time. Why? Because when you get rid of non-determinism in space, it suffices to exponentiate that and get the time deterministically. That's what we're doing here. Right? So that's Savitch's. That's one of the theorems. We didn't give it a name, but it's one of the theorems we showed earlier, that to simulate a certain amount of space, non-deterministic space, suffices to just exponentiate the time by keeping track of all the possible states that this space can be in, and there's an exponential gap between logarithmic and polynomial. So P is less or equal to NP. That's true because non-determinism is a generalization of determinism again. Same for this. That NP is in P space. This is non-deterministic polynomial time, and you can't use more than polynomial space if you only have polynomial time to use it. So that's true there. Exponential time, again, polynomial space and exponential time. That's similar to this result here, and so on and so on. So each one of these theorems, now each one of these containments, we just proved as corollaries from the previous results. How many are okay with that? Okay. So we don't know if any of them are proper specifically, but we do know that from the space hierarchy denseness theorem, that logarithmic space is not the same as polynomial space, and polynomial space is not the same as exponential space because there's more than at least an asymptotic jump between log and polynomial and exponential. So we know that this blue is not the same as this blue, and this blue is not the same as this blue. These we know, we can prove by its corollaries to the denseness theorem. We also know that log time is not the same as P because there's an exponential growth here from log to polynomial, and P is not the same as exponential time. Polynomial time is not the same as exponential time because, again, there's an exponential jump between polynomial and exponential, and all you need is a log jump to get more in the denseness of the time hierarchy. So we know that this green is not the same as this green, it's not the same as this green. That's why I color-coded them. We know that this blue is not the same as this blue, and it's not the same as this blue. So between this green and this green, at least one of these three containments is proper. How many get that? Because you have these two things sandwiched between these two green things, and this green is not the same as this green right there. So at least either L is properly contained in NL, or NL is properly contained in P, or log time is properly contained in L if log time and P are not the same thing, and you got set containments all the way out, and these are transitive. If A is a subset of B and B is a subset of C, then A is a subset of C also by transitivity of set, subset containment. So at least one of these three is a proper containment, and possibly two of them are, and possibly all three. But they can't all be equal to each other. At least one of these three must be proper. Similarly, at least one of these three must be proper because L is not the same as P space. Between this blue one and that blue one, at least this one, or this one must be proper. Right? In other words, for sure we know that some of them are proper, we just don't know which. Because all the green ones are not the same as each other. All the blue ones are not the same as each other again. So at least one of these 1, 2, 3, 4, 5, 6, at least one of those 7 conjectures must be true. And one of them is P not equal to NP. And here are some of the others. They're all open. And some of them are more complicated, more harder to prove that P is equal to NP, because if you could show, for example, that P is the same as P space, then NP and P will automatically be equal to each other as a corollary, because they're sandwiched. P and P is sandwiched between P and P space, right there. Between P and P space, there's sandwiched NP between. So if any two are the same, all the ones in the middle between them are the same too as the two ends. So there's a lot of open problems here, not just P is equal to NP. I'm just showing you a few more. And there's a lot more than that even. There's literally hundreds of famous open problems, and of course an infinity of other problems that are not so famous, because the space hierarchies are, time hierarchies are all infinite, and you could also, it's easy to generate open problems. Just pick any arbitrary complexity classes, and chances are it's unknown whether they're the same or not. One is proper a subset of the other or whatever. So at least two of the above conjectures are true, not just one, but two of them, right? One of these must not be the same as the other. They must be proper, and of course here too, and so on. And chances are all seven are true. No two are the same. Nobody can prove it either way, but chances are none of them are true. Right? So this, and also this. Let me show you a weird result. So deterministic space n. We don't know if polynomial time is the same as deterministic linear time. We know they're not the same. But we don't know if either one is contained in the other, which is weird. Usually when these things are not the same, it's because one is properly contained in the other, and then that's why they're not the same. So if somebody proved that P is not the same as D space n, but nobody can show if one is a proper subset of the other, or they're just incomparable. It could be that they're incomparable. Neither one is a subset of the other. It could happen. So it could be that this is true, it could be that this is true, or it could be that neither one is true. Neither one is contained in the other, they're just not the same. That's kind of weird. And we also don't know if non-deterministic space linear is the same as deterministic space linear. But we do know that at least two of the following is true, and I'm relisting them here. There's about 7 of them. Right? That's what we showed on a previous slide and argued, that at least 2 of them must be true. But these are all open problems. So there's a lot of open problems, relatively few answers in complexity theory. Again, the reason is it's hard to prove lower bounds. It's hard to prove that something is impossible to do. It's easier to prove it is possible to do. Easier, not necessarily easy, just easier than prove an impossibility result. Because to show something is possible, you should give an example, you're done. Something that works. To show it's impossible, you have to show that no way in the universe of infinite number of possible ways could possibly work. And that's a tall order, generally. You have to argue very generally. So again, back to this touchstone of the Chomsky hierarchy, now we've seen, a lot more of this regions that we haven't seen before, right? And so let me just show you what else is going on here, just to codify it into this touchstone, image that we've seen all along, right? So, of all the languages, now we got P and NP. Here we got the equality of polynomial space, non-deterministic polynomial space, and here are some infinite hierarchies. Now we've seen the denseness theorems, right? So there's an infinite hierarchy within P. There's linear time, quadratic time, cubic time, and these are all different. How many get that? So I'm representing it now as this infinite hierarchy in purple. I technically should represent it as lots and lots of ovals inside P and outside this, but that will make the diagram very messy. So I'm representing it like this now, showing it as an infinite hierarchy right there. And all these levels of this infinite hierarchy, they're all different in one another. Each one contains an infinite number of languages, and they're all between here and P, all inside P, corresponding, for example, to all degrees of all the polynomials. And in fact, even between the degrees, there's more. So here I'm diverging from the Venn diagram-ness nature of this diagram. So this purple is no longer a Venn diagram, because technically all these purple ones should encompass all these circles here. And then within NP, there's an infinite number of classes there too. And within context sensitive, there's an infinite number, and within polynomial space, there's an infinite number, one for every exponent. And in fact, even between the exponents, there's even more because it's really dense. So there's infinite hierarchies all up and down this chart. Between exponential time, take a different base of the exponent, 2, 3, 4, or even 2.001. That's more than 2. And there's an infinite number of levels there. And so on and so on. Right? Within exponential space, there's an infinite number of levels. So now we can even fill in more details in this chart, and things are getting pretty hairy. And just so you don't think that these are the only levels here, there's lots of other descriptive hierarchies and complexity hierarchies I'm not even showing you that we haven't even discussed, and they're all over the place too. For example, even within regular languages right here, you can have infinite hierarchies within the regular languages. And one of them, for example, is the star height. Star height, the clean closure. So it turns out, if you only have one star that you can use in your regular expression, you can represent an infinity of regular languages, but some languages will require more than one star in their representation. Some will require 2, some 3. And as you increase the number of stars, you get more and more regular languages, especially if the stars are nested. So the nesting of the star is called the star height of the language. So even within the regular languages, there's infinite hierarchies. And so even within the context-free languages, there's LR1, LR2, LR3 languages. How many heard of those? They come up in compilers. How many characters you have to look ahead? How many tokens you have to look ahead to be able to using a PDA or context-free grammar, recognize a particular language or generate a particular language. So the infinite hierarchies within the context-free languages, deterministic or non-deterministic. Yeah. Oh, what a time to crash the program. Just when it was getting good. And like I mentioned, the regular languages, infinite hierarchies there. Within the recognizable languages, there's infinite hierarchies there as well. Let's just finish this picture and yeah. All right. So we looked at these infinite hierarchies. And for example, here's the star height hierarchy within the regular language, infinite hierarchy, each one having an infinite number of regular languages. Even within the finite languages, you could impose hierarchies, like the size of the language, for example. Even within finite languages could have 2 strings, 3 strings, 4 strings, and so you can have a hierarchy there too. So there's a lot going on. And again, there's hundreds of other things that won't even fit on this slide that go on as well. And we'll get to some of those too. Not all hundreds, but a few more, so you have a taste. So this is a tip of a giant iceberg. It's hard to even imagine how much more there is. You can spend a lifetime studying these things. You can do PhDs on these subjects, and people still do. And discover new things every month. There's entire conferences on all this stuff after all these years. This is all started by Turing. And even this Turing degrees is an infinite hierarchy right there. That's uncountably infinite, not just countably infinite. And recognizable languages, there's an infinite hierarchy right there as well. Okay, so any questions or comments about any of this? Now you're seeing more of this big iceberg, and more of this diagram that we've seen all along, and more details here. And there's a lot more to that than even you're seeing here. Thoughts, comments? Yeah.
How much of the infinite hierarchies is purely because it's a continuum? There's gonna be some different set of languages at some point, and how much of it is there's a qualitative the algorithms that accept these or
Oh, there's plenty of practical consideration. Like for example, even within P, there's algorithms that run in linear time, in square time, in cubic time, and even between n log n time. It makes a big difference if an algorithm is in the first level or second level here, whether it runs in linear time, quadratic time, or cubic time, or even n log n time versus quadratic time. If you can sort in n squared time, that's not so cool. You can only sort so many things. But if you sort in n log n time, that's better. So yeah, there's a lot of practical considerations at every level of how fast you can do things, and doing things faster with less time or less space is not just interesting intellectually, it's also very practical. There's a lot of problems we're trying to solve every day that, for example, it turns out the game of Go, if you generalize Go to an n by n board, you know, the ancient Asian game of Go, it turns out it's exponential time complete, actually. And Google just solved it heuristically just recently, a year ago, using a program called AlphaGo that beat the world champion in Go. Before that, they couldn't solve it very well. And it's an exponential time complete, which is worse than polynomial space complete, which is worse than NP-complete. So we try to solve problems every single day that are way out there. And the faster you can do that with less time and less space and better heuristics, the better off we are. For example, matching the problem of I give you two regular expressions and I ask you whether they're equivalent or not, whether they generate the same regular language. Turns out that's exponential space complete. That's worse than exponential time complete, which is worse than polynomial space complete, which is worse than NP-complete. It's like 3 or 4 levels removed above NP-completeness. And NP-complete problems are already hard, you know, traveling salesmen and scheduling and, you know, satisfiability, and we'll talk about that separately, about NP-completeness. So yeah, we try to solve problems way out there every single day. You know, somewhere out there is probably the problem of autopilot for cars. You know, I'm sure it's not polynomial time. The best you can do is hope to have some heuristics, and these heuristics we bet our lives on every time we get behind the wheel of every time we let an automatic self-driving car drive us. More and more people will have that experience as time goes, beginning 2 years ago, because there are already some on the road. Okay, what else? So that's a big universe out there. A lot of complicated objects out there. Infinite number of levels, and each one is infinite number of languages at each level. And I'm going to jump ahead because I don't want you to wait a week to see this picture. There's a lot between now and then, but the Complexity Zoo it's a website, and it lists some of these classes, context-free languages, and all these are live links. If you click on one of them, you get a whole wiki page about this class, its properties, its relations to other classes, what it means. Here's deterministic space, exponential space, logarithmic space. Here's non-deterministic polynomial space, and here's NP. Here's P, right? They're all alphabetized. So literally, there's hundreds and hundreds of classes, all which have names. And of course, there's an infinity of classes that don't have names. These are just ones that are so often studies that we give them special names, right? It's called the Complexity Zoo, and so far it has about 500 different classes. And this diagram shows you subset containment. So every arc in this graph shows you a subset containment, a Venn diagram relation to previous ones. So this is all the class website. So here I'm showing you the top. Here are all languages. This is 2 to the sigma star up there. And I'm showing you now in animated form all the other classes, right? So some of the classes here's NP flying by, right? Here's P, and of course there's other classes in between. And these arcs, again, are subset containments. So this is on steroids, the diagram I kept showing you all along with the colored containments, the Chomsky hierarchy. Here's a bigger picture. Of course, there's so many here that it's hard to see what's going on unless you kind of squint your eyes and look at it. On the website, you can blow it up on your screen, and all this becomes live. If you click on something, it shows you all the things kind of highlight above it that it's contained in. And if you click in another way, it shows you all the things that it contains, and they all get colorized. And it's really amazing to see it live. So I'm now focusing on just a few of them. Here's 2 to the sigma star, that's everything. Here's the recognizable languages, here are the decidable languages, exponential space, non-deterministic exponential time, I'm just highlighting a few that we know and love and talked about and highlighted, but there's many, many others that we haven't talked about. And here's the next piece of the diagram, and here's polynomial space, P space. Here's the polynomial time hierarchy, we'll talk about that separately. Interactive proof, IP. We haven't talked about that yet. Non-deterministic polynomial time, NP, we know and love. Here's P itself. and non-deterministic linear space and linear time, and then going down to the bottom, here's a few more classes from P and below. Here's the context-free languages, context-sensitive languages, deterministic context-free, deterministic logarithmic space L. Here's the regular languages, pretty close to the bottom. The bottom is just the empty set. There's nothing there. And as you go up, you get more and more complicated languages. So this is a much more detailed picture of the one I've been showing you all along. Even though the one I've been showing you all along getting more and more hairy and detailed and complex, there's even more detailed, refined, complex diagrams out there. And this is a nice website. I urge you to go into it for extra credit and see not just my version of it, but the actual version of the complexity zoo. And it's just a beautiful thing to see it live with all the live links and the wiki pages, and you can easily navigate around. This was created by Scott Aronson, by the way, that book you're reading, and who can name the bigger number? How many remember that article? Had you read at the beginning of class? Now you can appreciate that article better, because it talks about the busy beaver function, which is not computable, and implications of what if you can compute that, and so on. So there's a lot going on, and I urge you for extra credit to go in there and play with it. Let me know what you think, what you learn. It's very cool. All right, so that's where we're going in the next lecture or two, and then we'll talk about NP-completeness for a while, and heuristics, and approximation algorithms, and it'll be fun. All right, so we'll see you next time.